Hello and welcome to my talk on maximum shallow clique minors and preferential attachment graphs. I'm Jan Dreyer and this is joint work with Philipp Kuinke and Peter Rosmanit. In our work we present a structural decomposition of preferential attachment graphs and show that these graphs are in the limit somewhere dense, which means that many of the algorithmic techniques developed for sparse graphs are not directly applicable in preferential attachment graphs. I'm going to start with an introduction to the preferential attachment model. If you're already familiar with this model, feel free to jump to 4 minutes and 30 directly to the results. The complex networks that we observe in the real world, they have some shared properties. They usually have low diameter, they often observe clustering, and they mostly have an inhomogeneous degree distribution. In a social network, for example, there's usually a small number of very active users which have tons of followers, while the average user has a relatively low number of followers. The relationship between the degree of a vertex and the number of vertices which have this degree has often been approximated by a so-called power law distribution. And the preferential attachment model has been introduced by Barabasi and Albert and tries to explain this behavior. It tries to explain how a network reaches the degree distribution that we observe in the real world. Let's start by describing how the preferential attachment process works. It is an evolutionary random process. It means it evolves a random graph over time, and in order to do so, it iteratively adds vertices v1, v2, v3, and so forth. And for every vertex that it adds also adds m edges. The random graph with n vertices and m edges per vertices is usually denoted by GNM, with n in the superscript and m in the subscript. Every time a new vertex is added, it is connected to the remaining vertices of the graph, and the attachment probability is proportional to the degree of the existing vertices. So if a vertex has higher degree, then it is a higher chance there that a new vertex is added and connected to this vertex. So we start with n equals to 1. So G12 is just a single graph with two edges. In our example, we choose m equal to 2. And then we continue by adding a new vertex v2. Now we need to connect two edges from v2 to the remaining graph. We do so by adding a stub in the beginning, and then we observe the degrees of the network. So v1 has a degree of 4 right now, v2 has just a degree of 1, so the total degree is 5. So since the attachment probability is proportional to the degree, the probability that the stub is connected to v1 is 4 over 5, and the probability that it's connected to v2 is 1 over 5. So now we make a random decision and see, okay, it is connected to v2, which would have happened with a probability of 1 over 5. So again, we add one more stub, and we see the total degree of the network is 7. So the probability of connecting to v1 is 4 over 7, and the connection probability to v2 itself is now 3 over 7. We make a random decision and see, okay, this time it got connected to v1. And we continue the same thing with v2. Again, we add a stub, make a decision based on the degree of the vertices, do it a second time, and continue with v4. And if we add 100 vertices, the graph will eventually look somehow like this. Here on the left side are the early vertices of the graph, and here these are the latest vertices. And we notice a tendency that vertices which already have a high degree accumulate even more degrees over time. So we have an effect called the rich get richer, and this influences the expected degree of the vertices. We notice that the ith vertex in this process has a degree of roughly square root of n over I. Okay, so let's next talk about our results. We characterize the asymptotic structure of preferential attachment graphs in the limit. So this means that in the limit with probability of 1, the graph will have a certain structure. And on the one hand, we observe that there's a logarithmically sized one subdivided clique. So here we have log n to the 1/4 many vertices, and each pair of them is connected by a private path. So every tuple of vertices, there is one vertex which is connected to both of them and to none of the others. On the other hand, if we remove log n to the O of r squared times m to the O of r, the graph becomes rather sparse. So we show that after removal of so many vertices, what we're left with is r neighborhoods that are treed with at most 2 extra edges. So this means if we fix a vertex and a ball around it with radius at most r, then the induced graph is a tree with at most 2 extra edges here. So the removal of a polylogarithmic number of vertices leaves the graph extremely sparse. So this means that the main source of structural complexity in preferential attachment graphs are the first polylogarithmically many vertices. They span one subdivided clique, but on the other hand, if we remove them, then we're left with a very sparse graph. Let us next talk about the algorithmic implications of this structural result. So many problems that are hard on general graphs become tractable once you restrict the input to more restricted graph classes, such as planar graphs, bounded degree graphs, or bounded tree width graphs. For example, 3 colorability is NP complete in general, but on bounded tree width, it suddenly becomes polynomial time solvable. But you can consider more general notions of tractable graph classes. For example, bounded genus generalizes planar graphs, and again, excluded minor generalizes bounded genus and bounded tree width. There's a notion of bounded expansion building on top of it even, locally bounded tree width, and the most general notion, at least for sparse graphs, would be nowhere dense graphs. Nowhere denseness forms some kind of natural barrier for algorithmic use. A graph class is nowhere dense if and only if it is not somewhere dense, and while many problems are solvable on nowhere dense graph classes and we have a rich algorithmic toolkit for them, on somewhere dense graph classes the situation is much harder. Our results imply that preferential attachment graphs are in the limit somewhere dense, which means that the algorithmic tools for nowhere dense graph classes are not directly applicable. But let us now describe what nowhere denseness and somewhere denseness means. So this is based around the notion of cliques and subdivided cliques. So here is a 4 clique. A 1 subdivided clique is a clique where on every edge 1 vertex is placed. Similar, a 2 subdivided clique. And at most 3 subdivided clique is a clique where on every edge at most 3 vertices are placed. Let now G be a graph class. We ask ourselves how large is the largest at most R subdivided clique contained as a subgraph of any graph in G. There's 2 possible answers. Either this number is bounded for every R, then G is said to be nowhere dense. And if this number is unbounded for some R, then it's somewhere dense. For example, planar graphs are nowhere dense because planar graphs contain no clique of size 5. As a minor, this means the largest at most R subdivided clique is at most 5 for any R. On the other hand, complete graphs would be somewhere dense because they contain arbitrarily large 1 subdivided cliques, or cliques in general. And now we may ask ourselves how large the largest at most subdivided clique is in a preferential attachment graph. And by the results that we discussed earlier, we know that there is a 1 subdivided clique of size at least log n to the 1/4. And on the other hand, we know that if we remove so many vertices, the graph becomes very sparse. This means if there is any subdivided clique, it needs to be almost completely contained in this gray part here. So this means that asymptotically, the largest subdivided clique lies somewhere between log n to the 1/4 and log n to the O of r squared m to the O of r. This means asymptotically, the largest at most R subdivided clique grows polylogarithmically with the graph size, so it is unbounded. And we can say that preferential attachment graphs are asymptotically somewhere dense. I will spend the remainder of this talk on sketching how to prove these results. So let's start with the lower bounds. Here we want to prove that there is a 1 subdivided clique of size at least log n to the 1/4. So let's assume we fix these log n to the 1/4 nail vertices. And we want to show that every pair of them will eventually be connected by a joining vertex. So if we proceed by fixing those two vertices, and we eventually find a vertex which connects them, and we show that this will eventually happen for every pair, then we get our one subdivided clique. Let's say we want to join the first two vertices, v1 and v2. What is the probability that the ith vertex vi will connect them? So in round I, the expected degree of v1 and v2 is roughly square root of I, so let's assume that this is their degree, and the summed degree of the remaining vertices is roughly I. So we can estimate the probability of v1 connecting to vi is roughly square root of I over I, equally for the other edge to v2. So the probability of connecting both would be roughly the product, which equals to 1 over I. So for the ith vertex, the joining probability is 1 over I. So what is the probability that those two vertices will never get joined after inserting n vertices? So this is expressed by the following product. So vi does not join them with a probability of 1 minus 1 over I, and we take the product until n, and you can see that this expression converges to 0. So the probability that they will not get joined converges to 0. In other words, they will eventually get joined with a probability of 1 in the limit. You can do a similar calculation if you assume that the degree in round I is slightly lower, as it would be, for example, for the first log n to the 1/4 vertices. There, if you plug in the numbers, you get an expression where here is a slightly larger number, but this still converges to 0. But so far, all our calculations assumed that the degree of the vertices in round I is roughly square root of I over log n to the 1/4 or something similar. But this is actually the case. So let's take a look at the actual degree distribution of the first vertex after 10,000 steps. It's plotted here. So the expected degree is somewhere around 100, as we may expect, but actually we see a very, very flat curve. So the degree after 10,000 steps of the first vertex is not well concentrated at all. So our calculations do not work the way we expect them to do. But let's observe something else. If we take the degree distribution of any set of vertices which has degree 18 after 100 steps and analyze the degree after 10,000 steps, we see that it's more concentrated. And even more concentrated if we assume a set of vertices which has degree 56 after 1,000 steps. So the observation is that if something has a high degree to begin with, then we get a very narrow concentration window. And this is the idea that we want to exploit. We want to find log n to the 1/4 vertices which have a relatively high degree after a relatively short period of time, such that the degree of these vertices will be closely centered around their expected value, and our calculations will work. And we do so as follows. We partition the first vertices into log n to the 1/4 many groups, which each contain log n to the 1/4 many vertices. The sum degree of all vertices in a group is now relatively stable, and we can use our concentration bound to show that after log n steps, each group has a sum degree of at least roughly log n to the 1/2. From each set, we take the vertex with the largest degree after log n steps and say this is a nail of the set. This gives us the log n to the 1/4 nails from which we want to construct a one subdivided clique, and each of them has a relatively high degree after log n steps. So now the concentration bound tells us that in round I, the degree of the nails is relatively close to square root of I. So it's close enough to square root of I such that our calculations as sketched earlier work properly. Next, I want to focus on the upper bounds, which state that after the removal of a few vertices, every R neighborhood in the graph is a tree with at most 2 extra edges. And I want to prove a simpler statement, but which uses the same ideas and techniques. I want to bound the probability that a 4 clique occurs after remove a few vertices. And what is the probability that a 4 clique occurs in the graph? we can use a union bound to distinguish between all ways in which a for-clique can be embedded into the vertices of the graph. So we say the first few vertices are not allowed, but any of the later vertices can be the location of the for-clique. So it can be embedded like this, like this, like this, like this, and many more ways. And we want to enumerate all embeddings and sum them up, which gives us an upper bound that a for-clique exists. So let us fix one embedding. What is the probability that the vertex number A, number B, number C, and number D together induce a for-clique in the preferential attachment graph? In order to do so, there needs to be an edge between all pairs of vertices. And you can show that the probability of an edge between the ath and the bth vertex in the preferential attachment process is roughly 1 over square root of A times B. Similar for all other pairs of edges. And now you may assume that in order to get the probabilities of multiple edges, you can multiply them. So the probability that all edges occur may be something like probability of AB times BC, CD, and so forth, which would be 1 over ABCD to the 3/2. Well, this is not quite correct because edges don't occur independently in the preferential attachment process, because let's say B is connected to A, then it increases the degree of A and in turn increases the probability that D also draws an edge to A. So we cannot simply multiply the probabilities of each edge separately, but you can prove that if you add another additional factor of log n to the k for some constant k, then you actually get a bound on the probability that the vertices A, B, C, D induce a for-clique. So now we have, for some fixed embedding, we have a bound that this embedding induces a clique. Next, we want to use the Ullmann bound over all possible embeddings. So we want to bound the probability that there is a for-clique in the graph after removing log n to the k vertices. So how can this for-clique be embedded? So for the vertex A, it could be any vertex from log n to the k to n. For B, the same, equally for C and D. And for some fixed A, B, C, D, we just bounded the probability by log n to the k divided by A, B, C, D to the 3/2. Now we can rearrange the term a little bit and we get the following. We just pulled out everything out of the sum as far as possible. And you can bound each of the 4 sums by something like log n to the minus k/2. So you get 4 times log n to the minus k/2, which is log n to the minus 2k times log n to the k, which is something that converges to 0. So we just bounded the probability of a for-clique after removing some logarithmic number of vertices and showed that the probability of the for-clique occurring converges to 0. And you can do a similar kind of proof, but with more bells and whistles, also for showing that every R neighborhood has at most 2 extra edges. And this concludes my talk. In summary, we've given a structural decomposition of preferential attachment graphs, which shows that these graphs are asymptotically somewhere dense. Thank you very much for watching my video, and I would be more than happy to answer any questions in the Q&A session of the virtual random event.